Hello, my name is Xavier, and this is my Lab 3 report on black holes and orbits. In this lab, I analyzed the motion of a star orbiting a black hole to estimate the mass of that black hole. And then I simulated a spaceship orbiting a planet and its moon to study how gravitational forces influence motion in multi-body systems. The purpose of this lab was to use computational modeling to apply Newton's law of gravitation and Newton's second law to real orbital motion. Part 1 focused on finding the mass of the black hole based on the motion of a star. Part 2 focused on using gravitational calculations to create a stable orbit of a spaceship, influenced by both the planet and its moon. Part 1 Mass of Black Hole. The fundamental principles. The main physical principles used here were Newton's law of gravitation, which states that gravitational force between two objects is equal to g times the product of their masses divided by the distance squared, and Newton's second law, which connects the net force to the rate of change of momentum. In an orbit, the parallel component of the force changes the speed of the object, while the perpendicular component changes the direction of motion. These two together explain why orbits curve instead of moving in straight lines. By rearranging the gravitational equation, we can solve for the masses of the black hole as force times radius squared divided by g times the mass of the star. In the GlowScript setup, I defined the constants, the gravitational constant, the mass of the star, and the unique c based on my email address, which generates a distinct orbital path. The time step was set to 1 Earth day in seconds to match the problem description. Then I used the data points of the star's motion to calculate the net force on the star at each step. By measuring the change in velocity over time, I found the acceleration, and then used the gravitational formula to solve for the black hole's mass at every position. From the simulation, the calculated mass of the black hole was approximately 9.97 e33 kilograms. The results were consistent across the orbit, with only minor fluctuations caused by numerical approximations. Overall, the star's trajectory remained stable and elliptical, matching what we would expect from orbital motion under gravity. Part 2 Orbit and Don't Crash. In Part 2, I modeled a system with a planet, a moon, and a spaceship. The planet was fixed at the origin. The moon started to the right of the planet, and the spaceship was placed on the moon's surface. I set the initial velocity of the moon so it orbited the planet, and then tested several initial velocities for the spaceship until it achieved an orbit that looped around both the moon and the planet without crashing. The velocity that worked best was around negative 10,000 in the x direction and positive 41,000 meters per second in the y direction. In the main loop, I calculated all gravitational forces: the force on the moon due to the planet, the force on the moon due to the ship, and the force on the ship due to both the planet and the moon. Using Newton's second law, I updated each object's velocity and position over time. This allowed the system to evolve naturally based on the mutual gravitational interactions between all three bodies. And the result was an orbit that lasted for 700 hours before finishing. The trajectory clearly showed that the spaceship was influenced by both the planet and the moon, which means the simulation successfully modeled the combined gravitational effects of multiple bodies. All right, possible errors. In approximations, it was most likely due to this being a simulation and it might not always work in the real world. And then also assumption that there are no outside forces acting on the system. And as far as accuracy, use trial and error of velocities to get the ship to not crash for 700 hours. And then could have used better and more precise velocities to stay closer to the planet. Discussion. What if part 1? How is the net force and its parallel and perpendicular components different from the rate of change of momentum in its components? So mathematically, F net does equal the change in momentum, but F net is harder to calculate due to having to sum up all the forces acting on the system. All dp over dt is just focus on the change in momentum of the system and change in time. So what if part 2? So to predict how the whole system moves, the model would need to include the gravity between all four objects, including the black hole, star, planet, and moon, since each one pulls on the others. But not all forces are equally strong. The black hole's pull affects the star the most. The star's pull controls the planet, and the planet's pull controls the moon. So the system is mostly shaped by a few strong pulls, while the smaller ones only make tiny changes to the motion. All right, and in conclusion, this lab connects theoretical physics with computational modeling. I found the mass of the black hole to be roughly, 9.97 E33 kilograms. And I successfully simulated an orbit influenced by both the planet and its moon. Through this process, I was able to clearly see how Newton's laws explain orbital motion and how multiple gravitational forces interact in a dynamic system. Thank you for watching.